Hello everyone, in the last class we learned about the connection between the turbine disc and shaft, and between discs. Today, we will learn about the connection between the turbine rotor blades and the wheel disc. Next, let these first learn about turbine rotor blades. Turbine rotor blades are important parts that convert the heat enthalpy and kinetic energy of high-temperature combustion gas into rotor mechanical work. When the blades are working, they not only have to withstand very high temperatures, but also the huge centrifugal force, aerodynamic force, and vibration loads generated by high-speed rotation. In addition, they also have to withstand corrosion and erosion caused by high-temperature combustion gas. Therefore, the working conditions of turbine rotor blades are very harsh. It is also one of the main parts that determine the life of the engine. The diagram below shows the profile of a turbine blade. It generally consists of three basic parts: the blade body, the intermediate blade root, and the tenon. Early engines rarely used intermediate blade roots, but engines developed after 1960 have adopted them more widely. Students may want to consider why turbine rotor blades have intermediate blade roots. The advantages of the intermediate blade root are: first, it reduces heat transfer from the blade to the disc. Second, the introduction of cooling air lowers the temperature of the blade root, tenon, and rim, reducing thermal stress within the disc. Third, the intermediate blade root prevents uneven stress at the blade base junction from being directly transferred to the tenon, improving the uneven stress distribution in the tenon, particularly improving the stress on the first pair of teeth. Next, let these look at the characteristics of the blade of the turbine rotor blade. Due to the high turbine airflow velocity, large turning angle, and thus large aerodynamic force, the blade profile of the turbine blade is more curved than that of the compressor blade. The blade body is thicker, and the cross-sectional changes along the blade height are also more obvious. Many turbine blades generally have a cooling structure design. In addition, the turbine blade usually has some special structures at the tip. The first special treatment is the blade tip chamfer, which involves removing a portion of material from the exhaust edge of the blade tip. However, when designing the blade tip chamfer, a maximum chamfer range must be specified to prevent excessive chamfers from affecting turbine efficiency. The purpose of the blade tip angle is to prevent cracks and breakage at the blade tip. More importantly, by removing a small amount of material, the blade's natural frequency can be altered to compensate for manufacturing errors that may cause some blades to fail to meet the specified frequency requirements. However, the blade tip angle clearly affects both the blade's strength and efficiency. The second special treatment is the blade crown. As shown in the figure, the high-pressure turbine blade of the turbojet 7 engine has a crown. The role of the crown is to absorb vibration energy by using the friction between adjacent blade crowns, thereby effectively reducing vibration. In addition, the adjacent blade crowns are combined into a ring shape to restrict the airflow to flow in the flow channel formed by the blades and the blade crowns, reducing the underflow loss and improving the turbine efficiency. However, the blade crown also makes the blade heavier. During operation, the centrifugal force caused by the blade crown increases the load on the blade body and the impeller. It will also cause additional bending moment and stress concentration at the transition between the blade crown and the blade body. Next, let these learn about the connection between turbine blades and wheels. The tenon of a turbine blade bears a large load, and the centrifugal force that the root of a blade has to bear is as high as 100 to 150 kilonewtons. In addition, the tenon works at high temperatures. Therefore, when designing the connection of the tenon of a turbine blade, in addition to the same requirements as those in the compressor, two aspects should be paid special attention to. On the one hand, the tenon connection should be allowed to expand freely after being heated to reduce thermal stress. On the other hand, the heat transfer of the tenon should be good so that the heat on the blade can be easily dissipated. Based on the above requirements, the connection method between the turbine blades and the wheel disc is usually a fir tree tenon connection. Fir tree tenons can generally be divided into two shapes: large arc with few teeth and small arc with more teeth. The fir tree tenon with large arc and few teeth has smaller stress concentration and good adaptability to changes in working conditions. The tenon structure has a certain dry friction damping effect and is relatively simple to process. The fir tree tenon with small arc and multiple teeth has uniform stress distribution and better temperature distribution, but it is more difficult to process and has more obvious stress concentration. The image shows the tenon shape of a WP6 engine turbine blade, which features 5 pairs of teeth. Currently, the trend is toward using a tenon with fewer teeth and a larger fillet radius between the teeth. In other words, a large arc with fewer teeth to reduce uneven tooth surface load and stress concentration. The advantages of using a fir tree tenon are: first, the fir tree tenon has a large cross-sectional area and is lightweight. Second, the circumferential dimension of the fir tree tenon on the rim is small, so more blades can be installed. Third, this tenon can be inserted into the mortise with a gap, allowing the tenon and the rim to expand freely after being heated. Fourth, the assembly gap of the tenon can be used to allow cooling air to enter and cool the tenon and rim. Fifth, it is convenient to assemble, disassemble, and replace blades. However, for the fir tree tenon with small arcs and multiple teeth, the fillet radius between the blade and the rim tenon teeth is small, resulting in severe stress concentration. In addition, this tenon has high requirements for processing technology. Students, in this class, we have learned about the structure and characteristics of turbine blades and the connection between turbine blades and wheels. I hope you can remember the advantages and disadvantages of turbine blade crowns and fir tree tenon connections. Thank you.